In the deepest parts of the ocean, where light never reaches and life depends on extreme conditions, something has been detected that should not exist: oxygen, not in residual traces, but in levels that suggest something is actively producing it in complete darkness. This challenges one of the most accepted foundations of modern science. Oxygen, as we understand it, depends on light. Without light, there is no photosynthesis. And without photosynthesis, there should be no continuous source capable of generating it. So, why are these signals appearing in places where everything indicates they should not be? To understand what is happening, we need to return to the basics, to what we believe we know about the origin of oxygen, and why for decades no one considered it possible to find it in the depths of the ocean. For decades, the explanation seemed unquestionable. Oxygen on Earth is primarily formed through photosynthesis, a process that depends directly on sunlight. Plants, algae, and certain microorganisms capture light energy and convert it into matter, releasing oxygen as a byproduct. Without light, this process simply does not occur. That is why, as we descend into the ocean, the expectation is clear. In the upper layers, where light still penetrates, oxygen is present, but deeper down, in total darkness, that supply should decline until it becomes nearly non-existent. This model is not just an assumption, it is the foundation for how we understand marine life, ocean chemistry, and planetary balance. And yet, in those same regions where the model predicts absence, instruments began recording the opposite. If oxygen depends on light, and there is no light there, then these readings do not fit within what we believe we understand. The first measurements did not raise concern. During routine expeditions, sensors placed thousands of meters deep recorded small variations in oxygen levels. Nothing that seemed extraordinary, nothing that justified questioning the model. In an environment as complex as the deep ocean, anomalies are common. Interference, calibration errors, minor technical inconsistencies. The simplest explanation was always the same: something in the measurement was not functioning as expected. But over time, something began to shift. The signals did not disappear. They appeared in different locations, under similar conditions, with different equipment. They were not isolated spikes. They were patterns beginning to repeat. Some teams chose to ignore it. Others, more cautious, began documenting these readings more carefully, not as proof, but as an uncomfortable possibility. Because if these measurements were accurate, then it was not an error. It was something that had not been explained. As more data accumulated, what once seemed like an isolated anomaly began to show structure. The oxygen readings were not random. They appeared in specific zones, at similar depths, under conditions where light was completely absent. Different teams, across separate expeditions, began recording nearly identical patterns, not just the presence of oxygen, but fluctuations that suggested active change, as if something were producing or releasing it intermittently. This changed the focus. The question was no longer whether the measurements were wrong. The question became, why were they happening in the same places? When a phenomenon repeats under controlled conditions, it stops being an anomaly. It becomes behavior that requires explanation. And at this point, the problem was no longer technical, it was conceptual, because if the pattern was real, then a process was occurring in the dark, one that no one had considered possible. The first response was to search for explanations within what was already known. If the phenomenon appeared real, then there had to be a cause compatible with existing models. The most immediate possibility was sensor malfunction, chemical interference, calibration errors, or contamination during sampling. Some teams replicated the experiments under stricter conditions. They changed instruments, reviewed protocols, isolated variables. Yet even with these adjustments, the signals persisted. Another possibility pointed to known chemical reactions on the ocean floor. geological processes that could release small amounts of oxygen without light. But when examined closely, a limitation became clear. These mechanisms were neither consistent nor strong enough to explain the levels being detected. Each explanation resolved part of the issue, but left another part unanswered. And this accumulation of incomplete explanations began to create a deeper tension. Because when multiple answers fail at the same time, what is at risk is not just the phenomenon, but the framework used to understand it. As conventional explanations lost strength, the investigation began to move into less explored territory, not in search of an immediate answer, but of mechanisms that, even if incomplete, could open a new possibility. Some studies began to examine chemical processes that do not depend on light, but on energy stored within minerals on the ocean floor. Slow reactions, nearly imperceptible, capable of releasing oxygen under very specific conditions, not as a constant event, but as something localized, dependent on the surrounding environment. At the same time, another line of inquiry emerged. Microorganisms adapted to extreme conditions, capable of using unconventional metabolic pathways where available energy is minimal. They do not produce oxygen like plants do, but they may participate in transformations that release it indirectly. None of these ideas, on their own, fully explain the observed pattern, but together, they begin to suggest something more complex. Because if these processes are occurring, then the deep ocean is not a passive environment. It is a dynamic system where chemistry, geology, and biology interact in ways we are only beginning to understand. And that opens an uncomfortable possibility that the oxygen being detected is not an exception, but a signal of something that has always been there, outside our model. As these possibilities began to take shape, the focus shifted away from oxygen alone. Attention moved towards something broader, the assumptions that have been used for decades to describe the behavior of the deep ocean. Much of what we know does not come from continuous direct observation, but from models built on limited data. Gaps were filled with reasonable inferences, based on the idea that certain processes simply could not occur without light. But if small amounts of oxygen can be generated or released in darkness, then those gaps are no longer as stable as they once seemed. This does not invalidate the existing model, but it makes it incomplete. And when a model is incomplete, every new observation stops being an isolated anomaly and becomes a clue, a signal that the system is more complex than it was simplified to be. So, the question is no longer how that oxygen is produced. The question becomes how much of what we interpret is based on what we believe we understand, rather than what is actually happening. If this phenomenon is not isolated, then oxygen is only one of the visible signals of something deeper. In an environment where direct observation is limited, many conclusions are built on expectations. And when something appears outside that framework, the natural tendency is to adjust it to what is already known, rather than question the model itself. But here, the opposite is happening. The data does not fully fit, and that friction forces a shift in perspective. Because if unexpected processes can generate oxygen under extreme conditions, then it becomes reasonable to consider that other mechanisms, equally subtle, could be occurring undetected. This raises a broader question. How many phenomena remain invisible not because they are rare, but because we are not looking in the right place or with the right tools? In that sense, the mystery of oxygen stops being a specific case and becomes a methodological signal, an indication that what we consider solid knowledge may depend largely on where we choose to look and what we expect to find there. At this point, the evidence does not point to a complete breakdown of knowledge, but to something more subtle, an adjustment, an expansion of what was thought to be complete. The oxygen detected in darkness does not redefine how the planet works on its own, but it introduces a variable that had not been considered. And in complex systems, even small variables can change how we interpret the whole. What began as an unexpected reading has revealed a limitation in the way observation itself was approached. Not in the instruments, but in the questions guiding the investigation, because for a long time, certain possibilities were not even considered. And when a possibility is not considered, evidence for it is not actively sought. What remains now is not a closed conclusion, but a direction, an indication that the deep ocean, far from being fully understood, remains a domain where what appears established may, over time, reveal another layer. And it is in that difference between what is assumed and what is observed that the investigation truly begins.